All right, folks, it's that time. Welcome back. We are going to do some more with the substitution. I got a few more examples, a little more exotic than last time, but maybe we'll start off with a non-exotic example. This is the u-substitution. It is kind of a complicated procedure, although once you get the hang of it, it can become easy, as with everything. Let's try something like this. How about that? The substitution is all about doing antiderivatives of complicated things, which you cannot do by other methods. This one is complicated by that third power. Actually, if it weren't for this 3, if that 3 wasn't there, you could just distribute the x to the 4 and then everything would be fine. But the fact that this 3 makes it quite a bit more complicated. Anyway, let's see if we can do this. So I hope that you all remember, you begin by choosing a piece of this formula to be u. So I'm going to choose the u, and the way the choice works, generally speaking, you choose the u to be the inside of something. But there's not really a rule about this. It's just something that you have to become accustomed to, looking at a formula and deciding what would be appropriate for the u. And that's where the more exotic examples are going to look at. But anyway, this one I think it's fairly clear. You should use the inside of these parentheses here. Just the inside, not including the third power. So it's 7 minus 2x to the 5 is what I'm going to use for the u. All right? Not including the third power there. Okay, and then the next thing we should do is figure out what is the du. That it's based entirely on the u. The du is always just the derivative of the u. So the du is, when I take the derivative of that, the 7 goes away. The minus 2x to the 5 becomes minus 10x to the 4. And then I put dx, because we always include, the dx is always part of the du. All right? And one last trick that we talked about towards the end last time, it is usually helpful to divide this constant. In your du, you often have a constant at the beginning, and it's almost always appropriate to divide this to the other side. So I'm going to write minus 1/10 du equals x to the 4 dx. Don't also move the x to the other side. This is just an equation here, with 2 sides, and I'm moving the 10 to the other side, but keeping everything else where it goes, where it already is. All right. Anyway, now we can continue with the substitution. So over here, the first thing I'm going to do, our goal is to replace all of this stuff with u's and du's. The first thing I'm going to do is just put u where it goes inside the parentheses there. So this is x to the 4 times u cubed, and then dx. That's just putting the u where it is. Next, I am going to rearrange this to sort of gather the u's to the front and put what's left over at the end. And the reason for doing that step is because now you can see what's left over is x to the 4 dx. And what is x to the 4 dx? Over here, you can see x to the 4 dx equals that. And so the next step of the substitution will be to replace, instead of x to the 4 dx, which is that, I'm going to write this because of that equal sign. So I end up with integral u cubed times negative 1 over 10 du. And this constant on the inside of the integral, you can bring all the way out to the outside of the integral. It acts like a coefficient. And this, now, the substitution is complete. I'm not done, but I have successfully rewritten the entire integral in terms of u's. There's no x's left. And that was kind of the point of this. The whole purpose of the u substitution is that you begin with a very complicated thing in terms of x. You turn it into a simple thing in terms of u. And I hope you agree this, what I have here, is much simpler than what we started with in terms of x. All right. Now we should actually do the antiderivative. The purpose of this is to simplify in inside so that you can actually do the integral now. And this is just u to the u cubed, which I do the antiderivative, it becomes 1/4 u to the 4. So this is minus 1/10 times 1/4 u to the 4. And because I did the antiderivative in that step, we don't put the integral sign anymore, and we do put the plus c. I hope you were putting the integral sign in all of the previous steps. It should be there until right here, because this is actually the antiderivative. In the earlier steps, I wasn't doing the antiderivative yet. All right, anyway, this is basically the answer. One last step, which is always easy to do, is you want to express the answer in terms of x, which is the original variable. And so how do we put x's back? This u is that in terms of x. And so we just replace u, sorry, it's off the top. We replace u here with that stuff. So I end up with minus 1/10 times 1/4. And now instead of u, I'm writing 7 minus 2x to the 5 to the 4 plus c, like that. This is my final answer. All right, this is the u-substitution. It looks like a lot of steps, and I mean, I suppose it kind of is. Once you get accustomed to it, you can probably do some of those intermediate steps in your head. But I'm going to write them all out. All right, and I will just remind you, you can always check your answer for these problems. How you would check your answer? Anybody remember? How would I don't think we need to go through the details, but what would you do if you wanted to check it? Yeah? Yeah, you take the derivative of the answer, and if you did it all right, you should get this. So the derivative of this answer should equal the function that you started with inside the integral sign. All right, that's the substitution. This I would describe as a fairly ordinary example, because what makes it difficult is choosing the u at the beginning. And in this case, it's fairly obvious by looking at this, and I say you choose the u to be the inside of something. There's really only one thing that you might choose in that case, and it would be the inside of the parentheses. All right? Sometimes it's not so simple, though. So I will say, generally, I'm just going to write this again. Generally, choose u to be the inside of something. All right? The inside of something. Now, the examples we've done so far, it has been the inside of parentheses or the inside of a square root sign, but it can be insides of other stuff. How about, here is an example. This is one involving an exponential function, x squared times e to the negative 2x cubed plus 4 dx. All right? How are we going to choose the u in this time? In the spirit of the inside of something, I'm going to choose the inside of the exponent. Just the inside of the exponent, not including the e, but just what you see on the inside. So u here is going to be negative 2x cubed plus 4. This is the inside of the exponent. Don't also take the e with it, though. Just the inside. All right? We should be able to continue this more or less like we did before. Can anybody say what's the du going to be? That's what I should do next. What do you say? Negative 6x squared. Great. And I think I heard her say, deep down in her heart, dx. You should always include dx as part of the du. All right? Excellent. That's the du. Because I know what good little boys do, I'm going to divide the 1/6 over to the other side. Divide the negative 6, I mean. So this will say negative 1/6 du equals x squared dx. Usually you're going to get a constant in the du part, and it's almost always appropriate to divide it over to the other side. All right, now we go back to the integral and try to plug stuff in and turn everything into u's. So the first thing to do is just put u directly where it is inside the exponent. So this I will say that would just be, x squared e to the u, right? That is placing the u where it goes in the formula. And then I will do my little sort of gathering step, rearrange a little bit. Just put the stuff with the u's first. E to the u times x squared dx. And now you look above. What do I do with x squared dx? if you've done it correctly, x squared dx should be here, and it equals something in terms of du. And so this x squared dx, I replace with negative 1/6 du. So this is e to the u, and then minus 1/6 du. And then, as usual, I'm going to pull the constant out of the integral sign. And then my sort of substituting and simplifying will be complete. Negative 1/6 e to the u du. All nicely substituted in terms of u's. All right? How do we continue? At this step, we should actually do the integral. I have not yet done the antiderivative, and so here I'm going to actually do the antiderivative. Here you have to remember some kind of rule about integral of exponential functions. You should have these formulas written like in a box somewhere in your notes. Does anybody recall? There is a formula for integral e to the x. Anybody remember?
Is it just e to the x?
It is e to the x, yeah. This is not one of our harder formulas to remember. Everybody knows the derivative of e to the x is e to the x, and so also the antiderivative of e to the x is e to the x. All right, so that's what I'm going to do here. This says e to the u. When I do the antiderivative, it becomes e to the u. It's just the same thing again. That's what this rule says. So, that, of course, the minus 1/6 stays like that. And then I get e to the u plus c. All right. This one is slightly confusing. You might feel like, what actually happened in this step? Like, it kind of nothing? Or did we just, the integral sign just goes away at this step? The answer is, I did the integral, but it turns out, because this is e to the u we're talking about, in this particular case, doing the integral actually doesn't do anything. All right? Anyway, the very last step is to replace the x's. So instead of u, I'm going to write here the original formula for x. So I write negative 1/6 e to the negative 2x cubed plus 4 plus c. That's that. All right. Any thoughts or feelings about that one? I have two more slightly weird examples, and then I got some for you all to try. Let's try. There are some cases in which you choose the inside of something or other, there's some cases in which there really isn't an inside of anything, but you can still make it happen. So here's an example. X over x squared plus 1 dx. All right? And the moral of the story for this one is sometimes in a fraction you can choose u to equal the denominator. In this sense, the inside that I'm looking at is like somehow the inside of the fraction or the inside of the denominator. If you see a fraction there, sometimes it is appropriate to choose u to be the entire denominator. Let's see what happens. In that, just take my word for it. U equals x squared plus 1. That would be the choice of the u. And then I do my du, as usual, is the derivative of that, which is 2x, followed by dx. And just because I always do, let's divide the constant. So that 2 I'm going to put on the other side as a 1/2. 1/2 du equals x dx. All right? And let's try to start plugging this in. So this thing here, first I am just going to put u where it is. U is the denominator there. So this now says integral x divided by u dx. All right? I just put u where it is, which is in the bottom. All right, and now I'm going to do some simple simplifying. At this point, I usually like to kind of gather the u's towards the beginning and put all the x stuff afterwards. Is that possible to do here? This is a fraction. What I want to do is put sort of some stuff here times some stuff here, including all the x's. I want the u stuff to go first and the x stuff to go second. Anybody see how you could do that? Yeah?
You could do 1 over u times x.
I like this. She says 1 over u here times x dx. Yeah, so in this case, the gathering things or rearranging things involves splitting up the fraction. I hope everybody agrees. If you have a fraction x divided by u, that's the same as 1 over u times x. This is how you would split it out. You sort of split out the denominator, of course keeping it in a denominator, and then the numerator is the other part. All right, excellent. And now, the next sort of thing that I would typically do here is look at x dx and try to plug that in based on the du stuff, and I do see x dx right here. So this will work. X dx is 1/2 du. So this now becomes integral 1 over u times 1/2 du. And then, as usual, we pull the constant out to the front, and the substitution is complete. 1/2 integral 1 over u du. Excellent. All right, we're not done at this point, but at least the substitution has seems to have worked, right? Now, the end here is we have to actually do the antiderivative. The antiderivative of 1 over u. This, anybody recall how to do that? You must have somewhere in your notes, again, in a box somewhere, you should have a formula like this. The integral of 1 over x. Of course, 1 over x is the same as x to the minus 1, right? I'm not saying that's the answer. I mean, these two things are the same function. Anybody recall what's the integral of that? You should have written this down somewhere.
Is it 1 over 2 u squared?
No, this is not a bad idea. You might think of trying the power rule here. Remember, if you look at it this way, x to the minus 1, you could try the power rule there. That means you increase the power by 1, it becomes 0. Then you divide by the power, which means dividing by 0. And at that point, you should decide that this is not the proper way to think about it. There is a special rule for the minus 1 power, or for 1 over x. Do you remember what it is?
It's ln times the absolute value of x.
Yeah, it is the natural log of the absolute value of x. When you see 1 over x, or 1 over u, or whatever, 1 over whatever, it makes a natural log when you do the antiderivative. This is an example where what you started with, actually, there's no indication that the answer has anything to do with logs or exponentials, but in fact it does. The natural log appears naturally. So this is 1/2 ln absolute value u plus c. All right, so in that step we used the old integral of 1 over x equals natural log absolute value x formula. All right, and then finally, that's not my final answer is to, as usual, you replace x's in the very last step. So my true final answer is 1/2 natural log absolute value u. Up there you can see u equals x squared plus 1. So it's there. There you go. That's my real answer. All right, the natural log sometimes comes up when you least expect it. Probably not in your ordinary life, but in your math class. All right, any thoughts about that? I actually did use the natural log once in my ordinary life. True story. We don't need to get into that though. Okay, I got one more slightly exotic one, and then I have some for you all to try. So remember, the general principle is the u should be the inside of something. Sometimes you want to choose the u to be the denominator of a fraction, even if there's no obvious like inside and outside. Sometimes, here's one other sort of special case, sometimes choose u to equal ln of x. If you see ln of x in your formula, sometimes it is appropriate to choose that as the u, even if it's not inside of anything. So let's try one like that. How about this? Integral ln x divided by x. All right. This one is kind of extra tricky because you might think, oh, it's a fraction, so I should choose the denominator. It turns out in this example, if you choose the denominator, it doesn't work. You can do the substitution, but the integral doesn't get any simpler. The whole point of the substitution is to make the integral simpler. But if you choose the denominator in this one, it actually doesn't make the integral any simpler. We should instead choose u equals ln of x. I gotta do the du. Anybody remember what's the derivative of the natural log? It is 1 over x. Yeah, this is why the integral of 1 over x is the natural log. The derivative of the natural log is 1 over x dx. Okay? Ordinarily, at this point, I would divide the constant, but there is no constant to divide across there, so I guess I'll just leave it like that. And let's try to start substituting. First of all, I place the u up top, like that, right? U over x, because ln x is u, so we put the u there. Now I'm going to do my kind of separating step where I like to write the u stuff first and all the stuff with the x's afterwards. Again, I have a fraction here, which I'm going to separate by splitting out the numerator from the denominator. The numerator is u, so it just looks like u, and then the denominator part gives me that, 1 over x dx. All right. And actually, the rest of this goes pretty ordinarily. This separation is a little weird, but now what am I going to do with 1 over x dx? Anybody see what I'm thinking? It becomes du, yeah. 1 over x dx is equal to du. So right here, I can put du. So this is integral u du. Excellent. And now we should actually do the antiderivative. This is maybe slightly weird or maybe very easy, depending on how you think about it. What's the integral of u? Just u? This is as if you were doing just the integral of x. Yeah? 1/2 u squared. Yeah, you think of this u as like u to the 1, and you just do the usual power rule here. I don't know if you were thinking about something about the ln's or whatever. Well, that ln stuff is behind us at this point. This is just u to the power 1, and so you do the integral, you get 1/2 u squared. Plus c, of course. And then to finish off, I replace the original variable, which was x. So my final answer is 1/2 ln x squared plus c. That's how it goes. All right. Any thoughts about that one? All right, I got some for you. Like I always say, in my opinion, these are quite difficult. So I have several to try. There's one. Very strange looking. X squared times 4 to the x cubed. Next. That one I decided to write the variable with a z, just because YOLO, am I right? It doesn't matter, you do everything the same way. All right, see what you think of those. Each one of these might take you several minutes, so don't feel badly if you think these are tricky. After this, we're going to move on to something completely different. If you want inspiration, the first one is similar to the one with the E that we did earlier today.
Yes.
Yeah, I think the variables just
Yeah.
should be
Thank you.
And then x squared dx.
Wait, are you doing all this?
Doing something else. Yes, yeah. So, and you should get just this. Well, because regular. I mean, that's the different definitions. Okay. That's good. So I start by putting the u in, like instead of x.
See, they're all
See what we can do first. How's it going here? Yes. Yeah, yeah. No, you should also. I would say to do the integer with parentheses, which amounts to.
Okay.
Yeah, that's great. So that, you should think of this as z to the minus 1 power.
Oh, LN. No,
That's
that's
the yeah, that's the word confusing. Z to the minus 1, and then you do the regular power. The minus 1 comes down.
So it's like that.
That's what you do, right? One of these is the
Yeah.
same as z to the minus 1.
So it's
You do the derivative of that.
the so it's not negative one. Like this is this and then derivative of this.
That's, yeah, this is that, you should really write
And then-
this here. And first put another equal sign. And now do the derivative of that, but
And then-
this to the front and equals that.
Just
You subtract one.
also subtract one, so we can have
This one?
This, yeah, you were looking in the right place, I think. Yeah.
So it would just be 4 to u, or 1 over ln 4. 4 into the c. Okay.
Still good here? Just everyone okay? Yeah. Yeah, some, this is.
Like, look at this
Power
because,
using.
we do this with it before, it just disappears.
No, I don't, it's just like,
Well, you're doing the integer of 4 to the power u. Yeah, and so this is like, I mean, you can think of it as like 4 to the x, and there's a formula somewhere for the equal of a to the power x. Yeah, so that's what you should do. Yeah, yours. This is.
Wait, no, I
It's
just-
4 to the power x.
I don't know.
Which is very
Yeah.
Yeah. That's the only one I got. That's one over
How's it going?
Don't forget to see.
I'm doing that right now.
Oh, yeah, how did you get your number?
This is pretty good. Should
Because I only got four to the two.
It's like 4 to the x. Like you have to go back to that form that we made. It was like, it's
Now,
like an
yeah,
a
the next
to the
step
x
we need to actually
is
do
1
is
over
integer.
ln a
It's
times.
it's 4 to the power x. You should,
Wait,
well, 4 to the u, but you should have a formula somewhere for this. So that's what you have to use. Okay.
Yeah, I think so.
Okay. Still not all right?
Yes, I have to.
Okay.
I don't think that's right, like,
So this is substitution.
Okay.
I just don't know if
You did that.
that's fine, because it's like, I think, originally I had this as two stretches, and maybe that's what I have.
There's no change.
No, it was, I changed it.
Okay.
I mean, I'm looking
And then
at
this one, I chose the inside of
That's
this.
good.
But, okay,
Yeah, this is all great.
okay.
So here, how do you do this? I think I would say parentheses and you take the next to
Okay, and then do the power. Okay, so we should use this denominator, we should
Yeah.
use the denominator, or
But then
which square two? Like
Yeah, that means
the
that
one
it's
that's
kind
E,
of a judgment call.
or the E one, or the X over, whatever, the E one, the Z's. Choose the one.
I was doing
Z.
it or something.
Okay.
This is
just take my.
Yeah, it's all great so far, so you should start doing substitutions by the first. Okay here? Yeah, that's great.
I'm gonna give you a few more minutes and then we'll talk about these, even though nobody's done yet.
This one, doing okay? This section is not.
I know, and now we can, like, stress.
Wow, that's the easy one.
What's the derivative one? I just did like the power.
That's all one. This is, think of this as C, there's no power.
I made it like the negative one. Cause I was like, I don't know how to do it. You know what I mean?
This is,
People think before I take this, how people take this and do it before it.
Or, yeah,
you
for what?
realize that
For the derivative.
I imagine.
Well, yeah, and well, yeah, and then it'll be
So,
negative, yeah.
That's kind of like.
yeah, well, you should just on this.
Oh, okay.
This is not a, it is a bad idea, but it's not,
Okay.
it's not morally, I mean, this one is confusing. Just give it a thought.
I know this is.
So sometimes, like, that's what will happen when you make a wrong choice. Just have to go back.
I'm like so tired, I do those things. Was it, I changed the or was it like a lot of things? It was like, it was actually funny. Yeah,
Did you get the first one?
yeah. I like multiply it.
Okay.
No, I got, yeah.
Oh, yeah.
Yeah.
It was the top, like, it was the last one. Yeah.
Yeah, that's great so far.
Okay, I didn't know.
Get anywhere here?
Yes. This one, yeah, right.
Down.
One, this.
Any progress?
Okay. So this, yeah, this example here, actually, of course, this is yeah, this one, this is all great so far. You can always move the constant outside. Yeah, or this, think about having to receive
I don't want to talk about it.
to some.
No, I was like, girl, no, I'm ready, so done. Yeah.
You should have a formula for that. So
I like hate it.
Any progress here?
I started with this one, but I don't think it's right.
Yeah, in this case, you should not choose. Well, just because. I think you probably, you can tell kind of after the fact, this is part of what makes things hard, is that you have to just kind of get used to choosing something. But if you chose this, then you get this, and you feel like,
Right?
that's how you can actually. So I have to kind of go back.
This.
Really?
Oh.
I like
When
feel
you
like I
here,
gotta
you
show
want to
my
choose
kids.
the side of it.
Oh, okay. I'm not.
You like my Z's either?
That's just.
No,
because I
it
like
like
the
really
getting hacks.
Yeah.
My motivation
I
is.
also
How's it
think I
going
like
here?
having the stuff.
Oh, this looks pretty good.
But I'm starting with the Monday, the 18th. Especially because it's on Monday, this
last one.
All right, let's go over these. I know not everybody's done. These, as you now know, can be quite challenging, and sometimes, you know, like I said, often the hard part is just knowing how to choose the U properly. And if you make the wrong choice, then you'll get stuck. And when you do get stuck because you made the wrong choice, you just have to go back to the beginning and try the other way. And when you're not used to doing these, it can be difficult to tell the difference between I got stuck because I made the wrong choice, or I got stuck because I just got stuck, like because I don't know what I'm doing anyway. But yeah, you have to get used to these kinds of things. But let's try the first one. So the first one here, most people, as I was going around, settled on choosing the exponent, which is x cubed for the u, which is good. Then the du is the derivative of that, which is 3x squared dx. And then I'm going to divide the 3. 1/3 du is x squared dx. And so this, I start to do my substitutions. X squared, 4 to the power u dx. I'll write the 4 to the u first times x squared dx. And then x squared dx is 1/3 du, so this is integral 4 to the u times 1/3 du. Move the 1/3 out. And this is the point at which most people got stuck, not knowing how to handle integral of 4 to the power u. For this one, it's an exponential function. The variable is inside the exponent, which means you need to use the special rule for integral of an exponential function. You should be looking in your notes for a formula that looks like this, where the a in my problem, the a is 4. But the formula, I mean, you know, people found this eventually, is 1 over ln a to the x plus c. So this is the integration formula that you need to use in this particular one. So that 4 to the u, when I actually do this, of course I have the 1/3, the 4 to the u becomes this stuff over here where a is 4 and I have u instead of x. So it's 1 over ln 4, 4 to the u plus c. And then the last step, as always, is to plug x's back in instead of u. So this becomes my final answer. 1 over 3, 1 over ln 4 times 4 to the power, whatever that was, x cubed to begin with. There you go. All right, this is the answer. Anybody got questions about that one? I saw people, almost everybody got most of the way there. I think this is a little sort of obscure integration thing that you have to recognize at the end. All right, okay, let's try the next one. E to the 1 over z. This one is also tricky. This one is tricky because I would say in this problem there are two natural choices for how you should choose the u. You could think I'm going to choose the u to be the denominator, which is z squared, or you could think I'm going to choose the u to be the inside of the exponent, which is 1 over z. Only one of these choices is correct. And how do you know the difference? The unfortunate answer is there isn't really a rule for this. You have to try your best to make a good guess, and if it doesn't work out, you have to realize that things are not going so well, and then go back and switch your guess. Maybe I will. Don't write this down if you just want to write the right answer. But if I had chosen wrong and did u equals z squared, can we just try and see what would happen in that case? In that case, I would do the du is 2z dz. That's the derivative of z squared, and then divide the constant, I suppose. 1/2 du equals z dz. And then what would happen when I try to start plugging in? I can make this e to the 1 over z over u dz. I could separate out the fraction as I like to do. But now at this point, I should realize that this is not going to work out because this and this don't look similar at all. And this is in this part of the procedure, this is when this part here has to match with this so that you can substitute in the du. So this is the point at which you realize you have made some bad decisions in life. I don't blame you for trying to choose that because it's not a bad idea necessarily. It just, in this problem, doesn't work out that way. So instead, we should choose the inside of the exponent. So maybe I'll leave that on my paper here. that's sort of a cautionary tale. I'm going to choose instead the inside of the exponent, 1 over z. All right? What's the derivative of that? Of course, 1 over z is the same as z to the minus 1 power. And so when I take the derivative of that, it is negative z to the minus 2 dz. Already, this is slightly confusing, just because you're so used to doing the antiderivative every time, you may have forgotten how to do the derivative of 1 over z, but it's that. Z to the minus 2 power dz. And in the spirit of dividing the constant, this minus sign, let's put it on the other side. Negative du is z to the minus 2 dz. All right. And now let's try to plug in the various stuff. So here, when I plug in, the numerator now says e to the u. The bottom says z squared dz. As usual, I'm going to separate out the fraction with the u stuff first and then the z stuff. It's e to the u first and then 1 over z squared dz. And this is the point at which I try to match up. I want to see this being the same as that. Are they the same? They are the same. It looks, I mean, they're not written exactly the same, but when you look at them, I hope that you realize they are the same thing. 1 over z squared is, in fact, the same as z to the minus 2. And so this thing in the red bracket equals negative du. So this is integral e to the u times negative du. And as usual, I'm going to pull the constants out front here. I have like a constant of a negative 1. So that minus sign can come all the way out to the front. And now everything is feeling good. All right? We just need to finish by actually doing the antiderivative. What is the antiderivative of e to the u? Oops. I keep the minus in front. But what's the antiderivative of e to the u? It is e to the u. I heard a whisper. Plus c. And then last step is plug back in for the u. So u is 1 over z. And so my final answer is minus e to the 1 over z plus c. That's what I would call a hard one. This might be the hardest of all the ones. Maybe I should put it last. Anybody have thoughts about that? Or questions? All right, let's just do another. I don't know if anybody actually got through all 4. Let's do this one here, just because I did want to proceed with something different. Maybe this last one I will leave as an exercise for the enthusiastic. So this one here. Did anybody try this one out? What did you choose for the u?
X squared plus 1.
X squared plus 1, I think is a good idea. That's the inside of something. If you see parentheses with stuff inside of it, that is generally going to be your choice for the u. Okay, the du then? What do you say? Somebody else tell me the du in this case? 2x dx, great. All right, I'm going to divide the 2 like I do. 1/2 du is x dx. All right, and we're going to try and plug stuff in here. I put, first of all, the u where it goes, which is on the bottom there, u squared. And now I'm going to separate out the u parts and the x parts. Can anybody say what does it look like when you do the separations? One over u squared. Yeah, great. Times x and then dx, of course. Yeah, great. That's the separating out the fraction. Next, we should try, hopefully, be able to substitute this piece, which does in fact equal that piece. So I can replace x dx with 1/2 du integral 1 over u squared times 1/2 du. This is the point at which I am now convinced that this is actually going to work, because I was able to correctly match up this thing and this thing. If that step hadn't worked, it means I would start to think to myself, either I messed it up or I made the wrong choice of the u. But it did, these two things did match up, so I'm feeling great at this point. Pull the 1/2 out to the front of the integral, like so. And now the substitution is completely finished. How do we do the antiderivative of 1 over u squared? Anybody get this far? One over u squared. This I would rewrite using a negative exponent. I would say this is 1/2 integral u to the -2, right? And then that thing you can do the ordinary integral power rule. You increase the power by 1, and then you divide in the front by that new exponent. So it says 1/2 first, and then I'm going to increase the power by 1. -2 becomes -1, and then I divide by a -1 in the front. So it's like that. And then last step is to plug in the x's again for u. So u was, I began with x squared plus 1. So 1/2 times 1 over -1, x squared plus 1 to the -1. There you go. All right. These, in my opinion, are quite difficult, as I've said before. So if these seem hard to you, then you are correct. Anybody got questions about that one? I think I want to move on rather than doing this last one, but maybe we could just start. Anybody have an idea? What would you choose for the u in this case?
1 minus 4x squared.
Yeah, I think you should choose the inside of the square root sign in this case. So for this one, if you wanted to work it out, you should choose that to be the u. And then I will just say, etc. See if you can fill in the rest of it. Although you're going to have plenty of practice on the homework with these. By the way, I just posted the homework this morning, so you should be able to check it out. Initial value problems and the u substitution. All right. This is all that I want to say concerning the u substitution. It is a very important and not easy to do trick for doing the integral of a weird function. All right? Great. So for our remaining 25 minutes, I want to go on to the next section, which is really completely different. A nice change of pace if you don't like the u substitution. The next section, remember the integral that we've been talking about, also known as the antiderivative. More specifically, it was called the indefinite integral. And when we first started talking about the indefinite integral, I said there actually is such a thing as the definite integral. And this is what I want to talk about next. The definite integral. And the definite integral is really completely different from the indefinite integral. We write it with the integral sign, but actually it represents something very different. It doesn't even represent the antiderivative at all. Why are they given such similar names if they're so different? It turns out there is actually a deep and non-obvious connection between the two things, but for today at least we're not gonna get to that. So the definite integral, this is all about it's about the area under a curve. The area under a curve is something that people care about. I don't know if this seems, probably this does not seem obviously useful, but what I'm talking about is if I have a function given by some curve, let's say y equals x squared, just because that's a pretty familiar function. The graph, of course, looks like a parabola. And I could ask you, what is the area under this curve? Let's just say like from 0 to 1. What I mean by that is if you sort of make this little shape here, I'm talking about this area of that weird curved thing. It's, I suppose, kind of like a triangle, but one side of it is a parabola, not a straight line. All right? The question is, what is this area? All right. This is a weird geometry question, I suppose. Something that everybody knows, like from high school or even before. Everybody knows how to find the area of an actual triangle or something like a circle or a square, or maybe you remember the area of a trapezoid or something like that. Anybody actually know the area for a formula for the area of a shape like that? The answer is No. This is not an ordinary kind of shape that people typically talk about. But actually, you can use calculus to find the area of a shape like this. And in fact, you can do the area of any kind of shape under any kind of function, provided that you know how to do the definite integral. That's what this is called. But anyway, this area here, I'm going to refer to this as the area under the curve of, this particular function, f of x equals x squared, from 0, I'll say specifically, from x equals 0 to x equal 1. So when I say area under the curve, more specifically what I mean is the area that you get sort of in between the curve and the x-axis. That's what I mean by under the curve. Of course, you can't go under the curve like down forever. That would be an infinitely long strip of area. So we wouldn't talk about that because that would be infinite. But this is what I'm talking about here. All right, and in this case, we write this, again, for reasons which we won't really get to today, but this is written as the integral sign with little numbers, 0 and 1 here, x squared dx. All right? We write this area also using the integral sign, even though this is very different from, so the integral sign without the little numbers means antiderivative. The integral sign with the little numbers means the area under the curve, which is totally different. Like this whatever it is, it's a number, right? Whereas the antiderivative would be a function with a plus c on it. All right? This is called the definite integral. The definite integral. The indefinite integral is the antiderivative. The definite integral is the area under the curve, the area between the curve and the x-axis. All right? Now this particular area is a very weird shape like that, so we don't expect the answer to be any kind of ordinary number. Although it may surprise you, I can remember when I first learned about this as a young lad, I was kind of shocked when my teacher told me, in this example, actually this area, by some kind of magic, actually equals 1/3. This is a true fact. The area under that parabola is equal to 1/3. I don't know if this seems mind-blowing to you. I can remember being very surprised by this because it's such a weird shape. I would expect the answer to be just some weird number like the square root of 2 or something like that with not like an easily recognizable number. It turns out to equal 1/3, which this should suggest to you that somehow there is some kind of fairly simple method by which you could figure this out. If the answer is so simple, it suggests that maybe there is a simple method by which you could deduce this 1/3. And in fact, there is a simple method, which we're going to talk about eventually. Although, for now, let me just say this is not obviously related to the indefinite integral, the antiderivative, which of course is 1/3 x cubed plus c. Even though we write them both using the integral sign, one is a number, the area, and the other is this function, the indefinite integral. Although you see a 1/3 here, it turns out the fact that there's a 1/3 here is why the answer is 1/3, but that's something we're going to talk about much later. For now, we'll discuss estimating this area. Rather than computing the area exactly, we're going to talk about estimating the area. And this is actually one of the big ideas of calculus, and this is one of the big ideas that goes back all the way to the beginning of calculus. And even before calculus existed, people had similar ideas like this. To estimate the area of a weird shape that you don't have a formula for, how can you try to figure out the area? And actually, this was an idea that I don't know if this originally comes from this guy, but this is an idea that you can see in the writings actually of Archimedes, who is a very very old, historically speaking, like many thousands of years ago versus, say, calculus was invented in like the 1600s. This is far older than that. But Archimedes did some stuff like this, and probably, I'm going to guess that some people in Asia did it first, like a lot of mathematics. But anyway, this was an idea that was done by Archimedes. Divide the interval into little bits and then draw rectangles, because everybody knows the area of a rectangle. So I'm going to try to draw a nice picture of what I'm talking about here. Let's say I'm just talking about the interval from 0 to 1, and I'm talking about this parabola here, right? And what I said, the concept here is I am going to, so the true area I'm looking for is that weird kind of three-sided shape with one side being a curve. I'm going to divide the interval into bits. And let's say, I said little bits. Let's say I'm going to divide it into 4 bits. All right? So these 4 bits, they would be, if I'm labeling my points, this is 1/4, this is 1/2, this is 3/4. All right? And I'm going to draw rectangles that, there's actually a couple different ways you could think of drawing in the rectangles. I'm going to draw it specifically rectangles that hit the curve on the right side. You'll see immediately what I mean by that. So what I mean is this first little bit here is this bit from 0 to 1/4. I am going to extend upwards into a rectangle so that rectangle hits the right side of the curve right there. So this is my first little rectangle. You take this little bit of the interval and just sort of drag it upwards to make a rectangle. All right? And I'm going to do that same thing for each of the 4 little bits there. So the next one from 1/4 to 1/2, I again make a rectangle that goes up and hits on the right side, which is where the 1/2 is. So this second rectangle looks like this. All right, the 3/4 one goes to here, I guess. And then the one all the way to the right goes all the way up. All right, we get 4 rectangles here. And then I'm going to say the total area of these 4 rectangles is an estimation of the area under the curve, right? I would say those 4 rectangles is an overestimation because they are bigger than the area under the curve. But it's still, I mean, it's something, right? The total area of these 4 rectangles is an estimation of the area under the curve. All right? And this was Archimedes' idea. Like I said, I don't know if he was the actual originator of this idea, but if you want to measure a weird shape, the area of a weird shape, you should try to express that shape instead by rectangles. And it's probably not possible to do it exactly in terms of rectangles, but like in this example, you make rectangles that are kind of close to the original shape and then add up the area of those rectangles. Let's try to, can we actually do this adding up the areas? This is kind of a pain if you really want the answer like using your calculator, but it's not so hard to work out these precise areas. So can I just say, first of all, each rectangle, the area will be the base times the height, of course, but they all have the same base width here, which is 1/4, right? These are all sort of tall, skinny rectangles, and the width at the bottom is 1/4. So each rectangle has width 1/4, and the heights are different, of course. What are the heights? Actually, the heights are determined by the y value of the function, right? Because that's how tall each rectangle is. It is determined by the y values of the function. That it's these 4 y values, which I'm putting with big dots, right? Those 4 y values. The heights are the y values And actually, we could say specifically what they are. They would be like f of a fourth, f of a half, f of 3/4, and f of 1, right? Those are the 4 y values that you would get from this function. And what is f in this example? Of course, f is squaring, right? So these are actually, if you wanted to write them, they would be like 1/4 squared, 1/2 squared, because my function that I'm talking about here is the squaring function, 1 squared, all right? And so if I were to write down the total area under all of these rectangles, so the total rectangle area is a sum. It's a whole bunch of stuff added together, each of the rectangles of the, base times the height, where each time the base in my example is 1/4 and the height is f of whatever, right? It changes as you go down the line. It's a sum of a bunch of things. Each of them look like 1/4 times f of something, all right? So in our example, our case, the area, the total area of the rectangles, which is an approximation for the curved area, is 1/4 times f of 1/4 plus 1/4 times f of a half, that's the middle point, plus 1/4 times f of 3/4, plus the last point, 1/4 times f of 1. And if you want to write out what those f's are, they're squares. So this is 1/4 times 1/4 squared plus 1/4 times a half squared plus, this is kind of tedious to write out, but it's sort of brainless. I mean, there's not a lot to it. All right, that's the actual, this is what you would get if you added up those things. And I plugged these into my calculator just in case you are wondering, and I got 0.46875. That's what you get if you actually add those numbers up in this example. All right. This is an estimation of the area under the curve. And this is, so there's a very specific way that we talk about these kinds of estimations. So this one, which I just did, this is, and you will see homework problems like this, although I'm going to hold off until next time around to put these on the homework. But this is called estimate the area using. So when you see problems like this in the book, they write it this way. Using n equals 4, this refers to the number of rectangles. There were 4 of them. And the right endpoints. This means, right as opposed to left. That means when I drew the rectangles, they go up until they hit the curve on the right side, all right? You could also do it so that they go up until they hit the curve on the left side. And it would be, you get a different answer, although it would be almost exactly the same procedure, all right? This is called estimating the area using n equals 4 and the right endpoints. Can we do the same thing using the left endpoints, all right? This is the kind of thing that, it looks sort of complicated. If somebody walked in right now, they might think this is very complicated, but actually it's not complicated, really. Using the left endpoints. So in this case, the picture looks like this. Again, I'll divide it into 4 pieces. So I get 1/4, a half, 3/4, and 1. That's 0 over there, of course. This time I'm going to make my rectangles go up to the left side. So like the rightmost one over here, you extend up until it hits the curve on the left side, like that. All right? You can see this time I'm going to get an underestimation of the true area because these rectangles, they don't hang over, they actually kind of hang under. Anyway, the next one looks like this. The next one looks like this. Each time the rectangle goes up until it hits the curve on the left side. And then the leftmost rectangle is kind of like this is like a stupid rectangle of height 0. It just doesn't go anywhere, but I can imagine it as a rectangle of height 0. All right? But anyway, we can still add up the area, and it's going to look almost exactly the same. So this way, the estimate is, okay, so the 4 points here, I'm doing the same stuff. It is still 4 rectangles added together. They still all have the same width of 1/4. The only difference is the exact y values, right? So this time the estimate is 1/4 times f of 0, 1/4 f of 1/4, 1/4 f of 1/2, and 1/4 f of 3/4, right? The 4 y values that I'm looking at in this case are the y values for 0, 1/4, 1/2, 3/4. All right? That's the only difference. And you can actually see, if you can, remember when we did on the right side, I went 1/4, 1/2, 3/4, and 1. This is almost the same. It's just I start at 0 this time, and I don't go all the way up to 1 at the end, right? But anyway, this one, of course, those f's mean squares. So this is 1/4 times 0 squared plus 1/4 times 1/4 squared, 1/4 times 1/2 squared, 1/4 times 3/4 squared. And this I plugged into my calculator. I got 0.21875. All right. So this one that we just did, this was using the left endpoints. All right, and that's an underestimation. So what we have is we got, when we use the right endpoints, we got an overestimate. When we use the left endpoints, we got an underestimate. So it means the true area is something in between those two answers, right? It's bigger than this 0.21, but it's less than this 0.46. I already told you, the true area is actually 1/3. All right, but anyway, this is the estimation using the left endpoints. Now these estimations are not very close to the true area of 1/3, which would be 0.33, right? This to me looks pretty different. What if you actually wanted to get better estimations? Now I'm not going to do this by hand, but this is sort of where we're going in the future with this. To improve the estimation, you increase the n. Remember, n represents how many rectangles we use. See if you agree. If in those cases, I used only 4 rectangles, and those rectangles were not all that close to the original curve. But what if instead of 4, I used many, many rectangles? I'm gonna go nuts here and make, I don't know how many this is, but maybe that's about 20 rectangles. Look how close the rectangle area is with the original curve area. If I make all these rectangles, let's say I'm gonna hit them on the left side. They look like this, right? Now it's still an underestimation because these rectangles, they don't quite fill up the whole area, but the amount that they're missing is actually very small, right? The amount that they're missing is way smaller than before, certainly. So now, when you do this with the rectangles, now the estimate is very close. To the true area, right? All right, I think maybe we'll leave it at that. So we're going to do a lot more of this kind of area calculations next time, which is a nice change of pace, I think, from the u-substitution, in my opinion. All right, hope you all have a good weekend. Please continue to make appointments with me to do extra problems, test problems. See you next time.